Title says I'm going to talk about diffusion and segregation of granular impurity in dense inelastic gas. And my study is going to be from a theoretical point of view, more concretely from a kinetic theory point of view. So let me first describe what is a granular gas. It's a system composed of particles that collide inelastically. The characteristic collision time is much shorter than the typical time between collisions. And the density is sufficiently low, so the system can be described through the Boltzmann or Enskog kinetic equations. So let me show you a schematic picture of the system. I have two different kind of particles. One is in higher concentration than the other one. So this one here, that is on a very low concentration, is what I call the granular impurity. And the other species is this one here, is what I call the granular gas. So my problem is, or the problem I'm interested in, is in determining if I shear from the boundaries from the system and heat and shear, where the impurity is going to go, if upwards or downwards. In this case, I neglect the effects of gravity because I am under the assumption that the energy input in the system is high enough, so I can neglect the effect of gravity. So let me show you a schematic picture of the point of view from which I'm going to try to solve this problem. If this was a molecular gas, then the collisions are elastic, and there is transfer of energy back and forth between the particles of the system, and this would be the situation of the typical thermodynamic equilibrium state. But I can take the system out of the equilibrium state if I input energy from outside of the system into the system. So I can take it out from the equilibrium state. But what happens in a granular gas? In a granular gas, again, I have transfer of energy back and forth between the particles of the systems, but also there is a sink of energy continuously going into the internal dynamics of the particles of the system that is never coming back. And for this reason, if I don't input any energy in the system, then the temperature of the system is continuously decaying, and that's when I have the well-known homogeneous cooling state if the system is homogeneous. But most kinetic theories are based in a development taking this as a reference state. But this state has an inconvenience, I think. One, it never happens in real experiments or real situation, and two, it's unstable. So the point of view here is, if anyway a granular gas is a thermalized system, why not consider as a reference state just one that takes into account the external energy input that in any case is going to happen. So that's what I'm going to do. And again, this seems also a natural choice because the energy sink is compensated locally here by an external energy input. So this global picture is more similar to this situation in the molecular gas than this. Okay, so that's a point of view from which I'm going to try to solve this problem. So if I look for the segregation criterion from the mass flux for the impurity in a steady state, I get something like this, where this is a homogeneous parameter that usually is called thermal diffusion coefficient, and this is the logarithm of the granular temperature of the granular gas, and this is the logarithm of the relative density of the impurity compared to the density of the granular gas. So this gives me a relation between this gradient, and depending on the sign of this coefficient that is going to be homogeneous, I can determine if the impurity is going upwards or downwards. Obviously, this coefficient here, the thermal diffusion coefficient, depends on the diffusion coefficients of the granular impurity, and I need to resort to kinetic theory in order to calculate the value of this coefficient. So usually, this is done by recurring to the Chapman-Enskog method. That is, as you most probably of you know, is based on a perturbative solution of the distribution function for this single particle, where the perturbation parameter is indicates the order in the spatial gradients of the hydrodynamic fields. So if I neglect all terms, but just the zero order term and the first order term, I will have the so-called Navier-Stokes description. This is what I'm going to do. But again, this is why is, I think, useful the picture of taking into account as the reference state, the one that takes into account the external energy input instead of the homogeneous Coulomb state, because this reference state is going to be closer in general to a steady state with imposed spatial gradients. So in general, this F1 is going to be actually small if I take this as a reference state instead of the homogeneous Coulomb state. And this is what I'm going to do. So again, for a molecular gas, this would look like this. The zero order balance equations would look like this, and for a granular gas, it looks like this. It's all the same except for this term, the sink energy term. So what I'm going to do is this. Instead of considering this, consider this. So I consider the external energy input here. So this partial derivative is going to be zero, just like in the molecular gas. So by using the coefficients that result from this view, I have this energy balance equation for a steady state in the geometry of my system. And in this case, I expect this work better than a picture based on the homogeneous Coulomb state, and to solve the problem of granular segregation. So let me show you. This is the mass flux expression for the granular impurity, which depends on a series of transport coefficients. These that are the diffusion coefficients related to these gradients here. This is the granular impurity density. This is the granular gas particle density, and this is the granular temperature gradient. So when I apply this condition for the state that this should be equal to 0, this is when I get this condition here, where lambda, in this case, the thermal diffusion coefficient is, it's easy to show that is this. So the important thing here is to determine, I think, when you are studying segregation, to determine if it goes upwards or downwards. So the critical point is when this changes sign, means when this is 0. This is what I'm going to look for a steady state. So in this case, I'm going to use a steady state which has a linear temperature profile. This is a special state that can happen when there is a special balance between shearing and external temperature input. This has been shown recently. I'm going to take this one. And this is very far from equilibrium state for a granular gas. And for this state, this is what I take for this. This is the occupied volume fraction of the granular gas. This is the coefficient of restitution that in this case is common for the impurity and the granular gas. And this line is what the granular segregation that results from taking in as a reference state the one that takes into account the external energy input, and this is the one that results from taking as a reference state the homogeneous coolant state. And these are Monte Carlo simulations. So you can see clearly where the agreement is with. So this is basically what I wanted to show you. Also to comment that since lambda results from the diffusion coefficients, it's typically known in segregation problems that diffusion coefficients, you need to resort to the second Sonin order approximation for the distribution function expansion. So as I can get a good agreement also for the diffusion coefficients, because I have here, this is the first Sonin approximation, this is the second, and the symbols are Monte Carlo simulations of the kinetic equations. This is for spheres and disks, for this value of the occupied volume fraction and the relative mass and relative size of the particles. And this is another plot of the diffusion coefficients. So you can see the first one in approximation is worse compared to the second one. So that's it. I wanted to be brief my presentation. So I'm presenting an alternate Navier-Stokes description derived from a reference state that should work better for non-homogeneous granular phase flows, which are actually what we are interested in for practical applications. We have verified this for segregation criterion for an impurity in a moderately dense granular gas, and third, the second Sonin approach is needed for accuracy with the simulations.
So I have a question. Using this kind of reference state, you lose the generality in the expressions for the diffusion coefficients, right? Because you have to know the external input energy. Mm-hmm. How can you extend it to a non-small problem like this?
Well, I don't think so. My argument is that this kind of reference state is closer to a steady state than the homogeneous coolant state. Actually, I think that taking the homogeneous coolant state as a reference state is losing more generality than this, because any steady state in its final state has an external energy input.
Yeah, but
it's going to be closer to a real situation.
But you have to know the energy input in
Yes.
order to calculate your coefficients.
Yes, I know.
So if the energy input is changing in your domain, then you have to know how the energy.
Well, the energy input or the form of the energy input is going to that information is going to come from the boundary conditions. That you need it too, because for example here in the segregation condition, you can see. Let me see. This you need to know the gradients to solve the problem, and you can solve the gradients once you have the boundary conditions.
See, but this is a local. If you have boundaries that are quite distant apart, then you would have to solve an additional differential equation for the energy input, right?
No. You just have the differential equations in the volume and the boundary conditions. Okay. So it's all you need to solve the problem. And depending on how you input the energy at the boundaries, then you have one solution or the other for the volume, profile.
I had kind of a related question. I was curious to know, your constant, is it constant or does it go as T?
My constant?
Yes.
Which constant?
The one that goes capital C.
C.
The next slide.
The energy.
Yeah.
Well, in the reference state, it is.
Oh,
It is constant because the system is homogeneous here.
Yeah,
Here.
that one, yeah.
It is. If the system is going to be homogeneous, it is going to be constant. But if it's not, for first order term, this is going to follow the profile of this, so it can compensate locally.
All right.
And balance. But as for the reference state, yes, it is constant.
Thank you.